floors. So today we'll be talking about unsupervised clustering of website URLs and clusters pattern recognition. So I'm Slim. I'm a senior applied machine learning engineer at Content Square. I've been here since approximately 4 years now, and I've been mainly working on semantic understanding of websites and web pages. So a few words about Content Square before digging into details. So Content Square is an experience analytics platform. So basically what we do is that we install a JavaScript tag on our client's websites, and then we're going to listen and save everything that is happening in order to basically do dashboards and KPIs for the client. So loading time of the page, time spent on a page, specific zone click rate, etc., etc. And then what we're going to do is that we're going to use those KPIs in order to give insights to the clients in order to improve the UX of his website. So let's start by stating the problems that we have, the problem that we have today at Content Square. So in order to do that, we need to basically understand what is a mapping. It's actually a Content Square concept. So a mapping is actually a way to map a web page into groups and into categories. So a mapping is a set of page groups. Each page group have a page category and actually is built using conditions on URLs. So we can see in the screenshot here an example of a mapping. So we have the page categories in red: home, product, cart, checkout, etc., etc., etc. And so for each page category, we can have one or several page groups in blue. And for each page group, we're going to actually build them using some conditions on the URL. So for example, here, path contains /p/, for example. How do we build page groups? So it's going to be, we are going to group into one page group similar web pages. So for example, if I am a shoe retailer and I'm actually like selling shoes, the product page on which I'm going to basically show my shoes is going to be the same. The only content that's going to change is the content of the product, the shoe. And so we can actually create a page group that's going to be all the product URLs of the shoes and say that this is the page group of product and the page category is going to be product. Why do we need a mapping at Content Square? So basically a mapping is a kind of a hierarchical view of the data of the web pages. And we need it actually in order to leverage it into a lot of analysis that we have at the company. So for example, here, I'm showing an example of what we call the journey analysis. So the journey analysis is basically we want to analyze, so the client, which is like the owner of the website, want to actually analyze and understand what are the typical user journeys in his website. Example, I am a user, I land on the home page, I go to the product page, then I want to the cart, and then I exit the web page, the website, for example. And we can't actually do that without actually configuring properly a mapping. How do we create a mapping? So in order to create a mapping, we're going to go to the mapping edition module inside the platform. And then we're going to start to create page groups one by one. So steps 1 to 3 is going to be around inputting conditions on the URL. So here we can see that we're inputting a condition on the path part. Classical parts of the URL are going to be the host, then the path, then the query. And then we're going to basically name it and give it a page category. Another example of a page group is the following. And notice here that we're using something that we call custom variables. So what's that? Custom variables is basically information that's being sent from the data layer of the client each time a user sees a URL on his website. So it's basically information that we can't modify, we can't standardize. It's just information that the client has and send us, and we can use, And so in our view at Content Square, a URL going to have 4 parts: host, path, query, and then custom variables, or what you call CVARs. It's basically like a query, a dictionary of attributes. And so in this example, I created 2 page groups. They actually cover 40% of the traffic of my website. And I'm going to actually create page group one after the other until I'm going to reach a majority of traffic. And so in average, we know that in order to have a good exhaustivity or a good coverage of traffic, we're going to create something around 15 page groups. And imagine that I am a client. I don't know how to input Boolean conditions. And I don't even know what are the conditions that I'm going to input. So what I'm going to do is that I'm going to browse my website in order to understand the URL structures, in order to know what are the conditions that I need to spot, and then going to start and inputting them in order to have the page groups. You kind of understood where I'm going with this. So basically, this is too manual, it's too long, it's too cumbersome, it's time consuming, and basically it's a human bottleneck for every feature that actually will depend on the mapping. So for example, if you take the journey analysis feature of earlier, we can't actually display anything until we have at least one mapping properly configured on the platform. So naturally, we want to automate all of this, or what we call auto mapping. And so what we're going to do is that we're going to have 3 goals. So 1, create meaningful page groups, meaningful from a business point of view. Then we're going to determine for each page group conditions that actually characterize this page group. And then we also want to determine the page category for each page group. So before going into the solutioning, let's see what's the data that we have in hand. So we crafted a data set of approximately 200 qualitative mappings. They come from approximately 200 retail clients, one mapping equal 1 client. And for each client, we have a tabular data. It's a URL data frame. So each row is a URL. Each URL is host plus path plus query plus CVARs. And so for each URL, we have the page group ID so that we know which URL actually belongs to which page group. We also have for the page group ID, the page category, and the conditions to create the page group. We also introduce some notations. So this is an example of a URL. So we have the 4 parts of the URL. And we call levels stuff that are in the path that are between slashes. So blah, slash, blah, slash, blah, those are levels. For query and for the CVARs, we have here, it's a dictionary of attributes. So we have keys and values. And at the end, we also call terms the union of the path levels, the query keys, and the CVAR keys. Okay. So now let's move to the solutioning part. So can anybody tell me what would be his approach to solve this task? Any ideas? Clustering? Yes, clustering, okay. So you'll be actually applying clustering on URLs, right? Yeah, can be one solution, okay. Anyone? Classification. What are you going to classify? So classifying page categories, for example, or? Yeah, so that's another solution, okay. So let's first talk about the failed solution here. Sorry, yeah. Links, what kind of links? Like, is it like actually like to URL linked by the user, like navigation, or what do you mean by link? But yes, we don't look at the content, but this is actually inside one website. Okay, so the failed solution. So basically here, what we tried, the idea is that we said, If we succeed to have a classifier of page categories, then we can actually create a mapping. And inside it, what we're going to do is that each page category is going to be equal to one page group. And that can be actually a pretty good start. So basically, we tried a lot of models, and the one that we kept was a deep learning model. So basically what we do is that we're going to model each part of the URL, so the path, the query, and the CVARs as a sequence of characters. And then we're going to basically have a representation vector for each of them that we concatenate, and then we're going to do a decision layer at the end. Unfortunately, this didn't really work. So it worked on some page categories, but it was basically not working on a lot of them. So basically we had good performance over 4 or 5 page categories over 15 or 20 page categories. So at this point, we started to wonder, do we really need to basically like use the big guns and try to learn patterns across all the websites? Do we really need to understand like what are all the patterns from all the websites, or do we actually need to focus to find a solution for each website alone? And this got us thinking of, let's try to maybe find some clustering solutions. And the hunch behind this idea is that for a given field in the URL inside one website, the cardinality of values won't be actually a lot. It would be actually finite and low. So for a given field, let's say like the first level of the path, is going to be maybe 2 possible values, 50 possible values, but not 1 million on one or more, you know, except for some given fields, but it's not the case for all of them. And so this got us thinking of, if basically we can come up with a solution where we can apply clustering on each website alone, we can actually succeed at this task. So the solution is the following. What we do is that we have the URLs of all the websites. We're going to sample them in order to have n URLs. So n equals 1,000 in everything that's going to follow. We're going to apply a pairwise distance metric using a URL distance. Hierarchical clustering, have a dendrogram. We are going to find a way to determine the clusters from the dendrogram, apply something to find conditions, and then so that we have at the end clusters with conditions. Notice that here we're doing sampling because this step is n squared complexity, and you don't want to compute a 1 million by 1 million matrix. So in the following slide, I'm going to shed light on some parts of this solution. Okay. So let's start by the URL distance. So what is the distance that we actually used to compare 2 URLs? So the distance is basically computed from the similarity. The similarity is basically based on field by field comparison. And this is only possible because of the hunch of saying the values inside the given field are not going to be a lot. They're going to be not that many. And so what we do is that we're going to say, you have 2 URLs, you're going to see if the host of both hosts are the same or not. For the path part, you're going to see if for each level, the level is the same or not. For the query, but also for the CVAR variables, we're going to see how many keys are in common. And then for the common keys in query and CVARs, we're going to see if the values are the same or not. We're going to normalize all of this over the levels, the keys of the values, of the queries and CVARs, and also over the variables. So that basically the impact of host, path, query, and CVARs is going to be exactly the same over the distance. And because of normalization, the distance is going to be bounded between 0 and 1. So let's take some examples here. So we have one example of a product URL, product URL also, a cart URL, and an empty URL. So we can see here that the distance between the empty URL and the product 1 URL is pretty high, 85%. We can see that the distance between the product 1 and cart and product 2 and cart 52% and 28% is very different, even though the first part is actually two product and the other part is actually a card. So this is actually something that is not really okay. So this is maybe something that is not that we don't want. But at this point we said, okay, let's keep this problem apart. Let's see like how this actually like performing, and then maybe this is something that we want to, solve. Next question. So how to determine clusters from a dendrogram? So what we did was a very dummy approach. We're going to grid search the number of clusters by basically trying different number of clusters from 10 to 40 on the dendrogram cut, and basically picking the number of clusters that's going to maximize the silhouette score. Next, how are we going to determine the conditions for a given page group? So this is actually an in-house system. It's not covered by the stock because I don't have infinity of time. But the main idea is very simple and it comes from the same hunch. In the given field of the URLs, you don't have too much values, different values. So what we're going to do is that we're going to say, if for a given field we don't have too many values, then those values are going to be the conditions. So basically, if you take an example, if the path level 0, we have two possible values, v1 or v2. The condition will be path level 0 equals value 1 or value 2. Simple, right? And finally, how are we going to evaluate the system? So we're going to assess the clustering against the page group ground truth clustering. For the sake of simplicity and only for the sake of simplicity, we're going to transform the clustering into binary classification to have a metric, because I don't have also a lot of time to cover what we did. So what we do is that we pick all the possible pairs of URLs inside one website, and then we're going to see if they are in the same cluster in the ground truth, and if they are in the same cluster in the prediction or not. And then based on this binary classification, we're going to compute the macro average F1 score for each client or website. And then we're going to apply a mean over clients so that each client has actually the same impact on metric. And the results are in, and they are not that good. So the results are 63% with a standard deviation of 11%. And we saw earlier with some examples that the URLs didn't make 100% sense always. So that clustering is basically very dependent on the quality of the distance. If the distance really translates into your business, the business meaning that you want, the clustering will be good. If it's not the case, you will have bad results. And so we saw in the previous examples that it was not always making sense. And so we wanted actually to try to understand what's happening. And so on the right, we have something that we call an interactive dendrogram. This is actually an internal tool from our company. Basically, it's the dendrogram. It's interactive. We can actually develop and collapse all the nodes. We can hover on each node to have various information on the cluster. And the most important part in this one, we're going to basically input conditions on the URLs. And then we're going to basically, at each time we are going to input in condition here, we're going to color the nodes of the dendrogram accordingly to how many, what's the ratio of URLs that actually satisfy the conditions that is here. So if it's actually dark green, it means that 100% of the URLs satisfy the condition. If it's dark red, it means it's 0%. And so in this example, we input page type equal product for this client. And we can see that given the colors, we can see that this condition is basically very distributed across all the dendrogram, which is something that is not good, because what we want is that we want actually these URLs that satisfy page type equal product to be actually in one cluster, and we want it to be very high in the tree, possibly, And so at this moment, we started to say, okay, we have a problem. And the problem is that intuitively, not all terms or fields in the URL have the same importance. Some of them mean something, some of them don't, like in this example. And so we said, okay, it's simple. We need weighting. And so this is solution 2. So in solution 2, we said, okay, we need to determine in one website what are the important terms. And so the question is, how do we actually determine the important terms in one website? So what we did is that first, we built what we call the universal important terms database. What we actually built it using the following steps. So we took all the conditions that built our mappings in the dataset. We extracted all the keywords that were used there, and then we manually labeled them if they are important or not. Important, basically, a term is important if it has a business meaning. So, for example, search, checkout, login, cart, account. And actually, a term is important if it's used in a lot of websites. So it means that this term is actually repeating a lot, And so we have this database, and we had in it something like 600 important terms. And so we use this database in order to determine the website important terms. So what we do is that we extract all the distinct terms in the sample URLs. Remember, terms are going to be path levels, query keys, and COR keys. And then for each term, we're going to consider it important if it's actually similar to at least one term in the important terms database. And the similarity is going to be a very simple criteria of is the Levenstein ratio of both terms more or less 80%. The Levenstein ratio being the Levenstein edit distance normalized over the length of both strings. And so using this, we can now have the website important terms, and we can use them in two ways, in two places. So the pairwise distance metrics and the determination of the clusters. So let's talk about the weighted distance. So basically, it's an improved version of the basic URLs distance with weighting over the important terms. What we do is that we're going to introduce weighting over the path levels, query and CVAR keys, query and CVAR keys values. The goal is to make important terms more important than others, so weight them more. But also we're going to introduce variable weighting. So the idea is that if in the path we have way more important terms compared to host, query, and CVAR, for example, maybe we want to actually like emphasize on the path over them, and so we're going to do variable weighting. This does not change anything about the fact that the distance still bounded between 0 and 1. And so the interesting part in here, so we took the same examples. We have the following important terms of the website. And so we can see first that the distance between the empty URL and the product one distance URL is now even more higher. It's actually maxed out to 99%. But more interestingly, we can see that the distance between the two product URL is now very low, and distance between each product URL and the cart is now very high. This is actually something that is intuitively good, and we wanted that. Another way to use the website important terms is in the determination of the clusters from the dendrogram. So the idea here is to say, if I have a cluster and that cluster has conditions that is using important terms, this cluster means something. So I want to keep it. And so what we do is that, so the important nodes in the dendrogram is going to be clusters that have conditions that use important terms. And the idea is to basically catch the important nodes in the dendrogram that are highest in the tree. And so what we're going to do is that we're going to start from the root of the dendrogram, and recursively we're going to develop the nodes in a top-down approach. Each time I stumble across an important node, I'm going to stop. And for some branches of the tree, I'm going to go down till the tree leaf, and I'm going to not find any important nodes. So what I'm going to do, I'm going to basically collapse them back. But basically, I don't want to lose my important nodes. So at some point, I need to stop. So here, for example, I develop, collapse. And then if I collapse back at the second level, I'm going to lose this important node. And this is something that I don't want. And so basically, we're going to stop here. And then at the end, we're going to say the state at which I stopped is going to be, the clusters are going to be the tree leaves of the state where I stopped. So this is the two main changes that we did compared to solution 1. And so we got the results, and they are way much nicer now. So 87%, standard deviation of 12%. And we can see on the same example here on the right that the page type equal product is actually now alone in one cluster and everything else doesn't have page type equal product. So it's nice. We can wonder now why it's actually only at 87% of performance. And this is basically a problem with the importance mechanism that we did on the terms. So if I give an example, in the universal important terms database, we were going to have the cart as term. And if I have on my website a term that is going to be carto, cart and carto, Levenstein ratio is going to be 88%. And so carto doesn't mean anything, but it's going to be, flagged as important. And this will actually introduce us some problems. And so the solution was to say, okay, we have something interesting here. Let's actually push it into production and let the user have the hand in order to refine this. So how we did this? So for a given website, we sample 1,000 URLs. We compute the distinct terms of the URLs. We compute the important terms using the inheritance mechanism. And then we're going to display all the terms for the user. And the important terms are going to be already selected. And then the user have the hand, and he can actually try to do some refinement if he see that this is not actually doesn't make sense. And then he can hit apply. We can also, for keys, see the values that can take the key. So when he hit applies, we have the list of the page groups. So in this example, we have 19 page groups covering 95% of the traffic. And we can see that these 3 page groups make sense. In the conditions, we have this one, which is actually product listing. This one is actually a home page. And the last one is going to be an order page. And we can even see in the steps, the different, in the last condition, the different steps of the order. So what are the next steps now? So let's recap. So we need a system to automate all the mapping creation, or what you call auto mapping. So we succeeded into create meaningful page groups, or what we call clusters, to determine the conditions that build each page group. But for the moment, we didn't actually compute the page category of each page group. But this is going to be one of the next steps. So what we're going to do for the page category inference for each cluster is going to be based on the same idea of the importance inheritance mechanism. So what we're going to do is that for each, universal important terms in the database, basically each term is going to be linked to one page category. And so applying the same mechanism of inheritance and importance, we can actually say, okay, this cluster using this condition that use this important term that actually have this page category. So it's going to be this page category. And the second point that we're going to do is also improve the importance inheritance mechanism. So we saw that there is some problems there. And so one of the ways that we're going to do that is that basically using this MVP in order to create mapping faster so that we can actually inject them back into the universal important terms database so that the mechanism of inheritance can be even more precise. And that's it for me. Thanks for your attention. And I guess it's now time for questions.
Is there any questions?
Thank you for presentation. Very nice to see such approach. Never saw it before, like with the weights and stuff. Just a question for my understanding: why it's important to have like a similarity higher between like empty URL and the URL with the query, and less between 2 products? Just to understand. When you showed the similarity score between empty page and the product page, you had a higher similarity. Between 2 products, it was lower. Why it's important to have such?
It's higher distance, not higher similarity.
Okay, higher distance, yeah. Sorry.
Because it's the inverse, actually. But, it actually comes back to the very beginning of the presentation, where we actually like build mappings mappings are going to be, let's see. So here, each page group is going to be linked to a page category. And so intuitively, we can't have one URL from the same page category that's going to have very different distance with another URL from another page category. So this is the first, I would say, for the first example. And for the empty URL, intuitively, if you give an empty object, you want the distance with that object to be high. If it's not high, it means that you're actually not doing stuff good in the distance. So that was actually like just an example of showing, okay, if I actually give you an empty URL and you're going to compute the distance with a real URL, you're going to actually have a high distance.
Okay, understood. Thank you.
But this was actually like, you know, it all depends also on the weighting that you're going to give also. So because in the second distance, you're going to weight variables. So in the dummy example where you're giving like 100%, 100, you know, weight on the host, and all the others are going to be only 1. If you compute the distance with between the empty URL and the product URL, you're going to have not that high of a distance, you know. So all comes down to what are going to be the weighting that you're going to use.
Thank you.
Thank you. Thank you for this talk. I wonder why you had to determine manually what was the important term, or why you couldn't use first TF-IDF or feature importance techniques, given that you already had an NLP approach first.
You mean in
Yes,
which one? In the to build the importance,
yes,
universal important database, yes, or to do the website important database terms?
The
first one
was about the first one, yes.
Well, I mean, we didn't have a lot of terms to assess. It was actually like manual annotation of something like 1.5K terms. And we managed to actually like annotate them manually in one morning, you know, very quickly to have like the response. So instead of actually trying to apply some, I would say, complicated technical stuff, manually, you can actually just have the response very quickly, you know. And this actually database is going to be used across any website. So.
Okay, thank you for your presentation. On the URL sampling part before the clustering,
yeah,
are you not? Don't you fear to miss some important URL? And also for the clustering algorithm, as the matrix size grow up with the number of URL, don't you try to use more optimized algorithm like herd movers distance or word movers distance to handle more URL when you're trying to calculate the matrix distance?
Very good question. So about aren't we afraid of missing important terms where we sample? Depends how you sample. And so basically, when actually we're talking about URLs, there is 2 types of URLs, I would say. They are URLs that are going to be not that much from a count point of view, but that they have high traffic. So for example, you take a homepage, it's actually 1 URL, but it have massive traffic. And then you have other types of URLs that are going to be very, very little from a count point of view, and they don't have a high traffic, but when you put them together, they are actually a lot. So for example, the product URL, 1 million products in your database is going to be 1 million URL, you know. And so what we do is that we sample URLs using 2 steps. So first, we don't want to miss the URLs that have high traffic. So what we do is that we're going to say we're going to sample n divided by 2 URLs weighted on the traffic, so that you don't miss URLs with high traffic. And then from the rest, we're going to sample n divided by 2 URLs randomly on the count, so that you're going to have Go URLs that are going to be in the second case. And using this technique, you actually have the best of both worlds, let's say, and you're going to have a good sample of URLs. So this is for the first question. And for the second one, you were wondering if 1,000 URL is not too little and you wanted to make it higher and optimize, the computations to make it faster. For me, the philosophy of this project is around the same hunch of saying URLs don't change that much. They are basically like built with code, and inside them, values are going to be, the granularity of the values are not going to be a lot. It's not like standard NLP projects where you're going to have like a lot of text, and actually you need 1 million of samples, and you're going to actually try to build something with it. This is a very special case. And so because you want to compute clusters that are going to be where you're going to actually try to understand the general structure of the website, saying, yeah, this is product pages, this is actually cart pages, etc. You don't need 1 million URLs. 1,000 URLs is actually sufficient, and you can actually have very good results with that. So if it's the case, why do we actually make life more complicated and have like, okay, I'm going to sample 1 million URL and I'm going to put, I don't know, like some engineers in order to optimize all of this to have like faster computations? No, sometimes simpler is better,
Maybe one last question, if there is some. Okay, thank you very much.
Thank you.